In this lecture, I'm going to review some basic probability concepts and then move on to Bayesian decision. The dictionary definition of probability is a way of expressing knowledge or belief that an event will occur or has occurred. For example, we say that the probability of getting a 1 on a die roll is 1/6. We say that based on our experience and knowledge that the numbers on a die are equally likely to be rolled. If we had additional information about an event, that may change our idea of the probability of that event. If, say, we knew it was a loaded die, where the face having the number 1 was lighter because of the large indentation, we would then revise our belief and say because the heavier side is more likely to land at the bottom, the number 1 is more likely to be on top. Another example is talking about how likely it is to rain today here in Philly. If we knew that on the average it rains about 80 days of the year in Philly, we would say that it is roughly 20% likely to rain today. We would revise, of course, our idea of this likelihood if we were given additional information about what particular season we are in, what the humidity level is, whether it is cloudy, and so on. Let us now go over some functions that we use to characterize the probability of an event. Probability mass function is a function that gives the probability that a discrete random variable is exactly equal to some value. Discrete means we have a limited number of values or categories. For example, we would define the probability of a die roll as a probability mass function. On the other hand, for a continuous random variable, we would use the term probability density function. That is because the probability of an exact value is not immediately useful. For example, weight is a continuous variable. The probability of a newborn baby being exactly 8.0 pounds would be an infinitely small value and not very useful. Besides, when we say the baby is 8 pounds, we unconsciously take into account that this is only an approximation and the baby is really 8 pounds, give or take 0.1 pounds. So rather than talking about the probability of having a weight exactly 8 pounds, we talk about the baby having a weight between 7.9 pounds and 8.1 pounds. If I have a probability density function for the weights of newborn babies, I can calculate the probability of a particular baby being between 7.9 and 8.1 pounds using the area under the curve. So the PDF tells us how densely the instances are populated around a value. Taking the integral of the PDF curve over a range gives us the probability that an instance would fall within that range. A special type of taking the integral is when we start from -infinity and talk about the area under the curve up to a certain value of the variable. And we call that the cumulative distribution function. For example, the CDF function at weight equals 8 pounds would give us the probability that the weight is equal to or less than 8 pounds. In other words, the CDF would tell us what percentile this 8-pound baby is among all the babies. Now let's look at the probability of two variables. The joint probability is the probability of two events happening at the same time, such as the probability that it would rain today and that I would go running today. In other words, the probability that I would go running in the rain today. Here are some common ways of showing joint probability of two variables. We can show it as A and B, A comma B, and A intersection B. An important concept used to combine additional evidence into our belief about an event is conditional probability. Conditional probability indicates the probability of an event A happening given that B is happening, such as the probability that I would go running today, given that it would rain. The conditional probability can be calculated using this formula, which sort of makes sense. Here is the probability that it would rain, and here is the probability that it would rain and I would go running. Together, this is the ratio of rainy days in which I would go running. In other words, the likelihood that I would go running on a rainy day. Conditional probability captures the dependence of one variable over another. Let's imagine that it rains 20% of the days. So probability of B is 20%. In a complete dependence case, say I loved running in the rain and would never miss out running in a rainy day, then the fraction of days in which there was both rain and me running would also be 20%. Therefore, the conditional probability in a complete dependence case would be 100%. On the opposite end, if my running was totally independent of whether it would rain or not, we would call these variables independent variables. Because there is no dependence, having known that B is happening does not change the probability that A would happen. So, probability of A given B is exactly probability of A, given that B has not really changed our idea about A. It has not provided any additional information. Consequently, the joint probability of two events when they are independent is just the product of their individual probabilities. And you can see that from the definition of conditional probability, where P of A given B is just A, you put PB to the other side and you get their product. Using a similar example, say I ran on average 50% of the days, and that it rained 20% of the days. If me running and it raining were independent variables, the joint probability that you would find me running in the rain would just be 50% times 20%, which would give me 10%. Now let's say you knew three things: how likely I would go running if it were raining, how many days on average I would go running, and how many days on average it would rain. And let's say you have been stuck in your office with no windows all day, and you cannot observe the weather outside. The question is, if I told you I ran today, can you figure out if it also rained today? And the answer is yes. We can do that by rewriting the conditional probability from the point of view of the other variable. So here the joint probability is written from the perspective of the variable A given B. We can also write it from the perspective of B given A times the probability of A. This allows us to pull out probability of B given A, which would be equal to probability of A given B times probability of B divided by P of A, all of which I have provided. Therefore, from these three pieces of information, you can find out the probability that it also rained today. This rewriting of the conditional probability from the perspective of two variables gives us the famous formula for Bayesian rule. Bayes' rule allows us to calculate the conditional probability of one variable using the conditional probability of the other one. This is a very important formula that we are going to use in the remainder of this lecture. So make sure that you memorize it, you know how to derive it, and you know how to make sense of it. Let's look at an example where we can apply the Bayes' rule. We are given the following facts. Suppose a drug test is 99% sensitive, which means it produces 99% true positive results for drug users, and that it is 99% specific, which means it gives true negative results for the 99% of the non-drug users. And additionally, suppose that only 0.5% of the entire population of people are users of the drug. Now, if a randomly selected individual tests positive, what is the probability that he is a user? In other words, we are asked what is the probability that a person is a user given that they've tested positive for the test. Let's solve this problem first using a chart like this and some example numbers. And then we'll use the Bayes rule. We should get the same answer with the two methods. Let's say we have 1 million people in the entire population. Our final answer won't change based on how many people we start off with. I'm just using 1 million people so I don't end up having to cut people in half. We are told that 0.5% of the population are drug users. That make 5,000 people. And the remaining 995,000 people are not drug users. By the way, putting a hat on a variable is a common way of representing not. Here U hat represents non-users. And we are told that the drug is 99% sensitive. So out of these 5,000 drug users, we correctly detect 99% of them, which makes 4,950 people, and the remaining 50 are drug users who are incorrectly tested negative. We are told that the drug is 99% specific. So out of 995,000 people, 99% of them are correctly detected as negative. So that makes 985,050 people. The remaining 1% of the non-drug users are incorrectly tested positive. That makes 9,950 people. It is important that you understand why these nodes are labeled the way they are. Each of these final leaves represent a joint probability. Here I have the probability of having a user and him or her testing positive. So that is the fraction in the population of people who are users and test positive. Here I have the probability of having a user and him or her testing negative. Here I have P plus given U. That means out of users, what fraction would test positive? Here I have PU, which means what percent of the population are users. If we go back to the question, it was asking us that someone tested positive, and what is the likelihood that they are drug users. If they tested positive, it could be because they are one of these 4,950 people who were drug users and tested positive, or they were a non-user and they were incorrectly tested positive. So they could be one of these 9,950 people. So if they were tested positive, we know that they could be one of these 14,900 people. Out of 14,000 people, the likelihood that they are within the group of 4,950 people is just 4,950 divided by 14,900, which gives us about 33%. So if we are told that someone has tested positive with this test, the likelihood that they are really a drug user is only 33%. Now let's answer the same question using the Bayes rule. To answer the conditional probability of P user given plus, which means the probability of somebody being a user given that they tested positive, we rewrite it as follows. P plus given user times P user divided by P plus. Now P plus was not given in the question. The question does not explicitly state the probability that any given person would test positive. Here we'll use an expansion trick. We'll consider different groups of people, drug users and non-users, and take the weighted average of the probabilities that a person within each group would test positive. And now we are ready to plug in the numbers. Probability that a user would test positive is 99%. The probability that a person would be a user in the entire population is 0.5%. Those are repeated at the bottom. The probability that a person would test positive incorrectly while they were a non-user is 1%, and the probability of non-users in the entire population is 0.995, which means 99.5%. And that gives us the same answer as we found before, 33%. Let me formalize the expansion trick that I used to find the value of p+. Whenever you are trying to find the probability of a certain value and it's not immediately available, you can use its summation of joint probabilities with another variable, but you have to consider all cases of that other variable. And you can do this for both discrete and continuous probabilities. As an example, say I'm trying to calculate the probability that I would go running on any given day. I can write this as the fraction of days that I was running and it was raining at the same time, plus the fraction of days that I was running and it was sunny, plus the fraction of days that I was running and it was snowing. And we'll consider that rain, sun, and snow are the only possible options. We have essentially taken the sum across all possible weather conditions of running together with that weather condition. And using the formula of joint probability that we learned before, we can rewrite each of these joint probabilities as the probability of running given that it is raining times the probability of rain plus the probability that I would go running given that it is sunny times the probability that it is sunny plus the probability that I would go running given that it is snowing times the probability that it is snowing. And again, we can write this in summation form as sum over all weather conditions, the probability that I would go running given that weather condition, times the probability of that weather condition. And we've essentially rediscovered the formula shown here. As a summary, I calculated the probability that I would go running on any given day by adding up the joint probabilities of running on a rainy day, on a sunny day, and on a snow day. Now you may be wondering how the probability and Bayes rule are useful in machine learning. Bayes rule gives us a very powerful framework for doing classification. We can formulate a classification problem as a problem where we are trying to find the probability of a class given an observation, an evidence. And when we have to choose among multiple classes, we pick the one with the highest probability given the evidence. Let's start with a simple univariate problem, meaning a problem with one variable. Say we are trying to classify a walnut as fresh or rotten based only on its weight. There may be other features such as the color of the shell, the sound it makes when you knock it on the table, but we'll ignore those features and assume that we only have the weight information. In order to build our model, we of course need some data about fresh walnuts and rotten walnuts. This data is best formulated as a class conditional probability, which means we'll have probability distribution function for the weights of fresh walnuts and a PDF of rotten walnuts. We'll assume that most of the fresh walnuts are heavier and the rotten walnuts are on the lighter side. If we overlay the two PDFs on top of each other, we may more clearly see which one has a higher probability for any given weight. For instance, the conditional probability of a walnut that weighs 1 gram is higher for the rotten class compared to the fresh class. We can summarize this overlay in the form of thresholds, such that for any given walnut, we can use a set of rules to classify it. For instance, we could say that if the walnut is less than 2 grams, it is more likely to be rotten. Between 2 and 3.5, it is more likely to be fresh. Between 3.5 and 4.5, it is more likely to be rotten. And if it is heavier than 4.5 grams, it is more likely to be fresh. Now this makes sense, but it is not entirely accurate. We should really be looking at the probability of having a class given a weight, not the other way around. The reasoning that we went over in this figure would have been correct if the background frequencies of fresh and rotten walnuts were the same. But we would end up not making the right choice if, say, we knew rotten walnuts were rare. The Bayes rule is how we combine the class conditional probability with the background probabilities of fresh and rotten walnuts. Let's see how we can correctly solve this classification problem. We have two classes, W1 and W2, which represent fresh and rotten walnuts, and will denote the weight of a single walnut with the symbol X. The a priori probability represents the background frequencies of the two classes. For instance, say among all the walnuts, 70% were fresh and 30% were rotten. Then P fresh or PW1 would be 0.7. The class conditional probability tells us within each class how the walnut weights are distributed. For fresh walnuts, the distribution of weights is the class conditional PDF of fresh walnuts. And for the rotten walnuts, the distribution of their weights is the class conditional PDF of rotten walnuts. The classification problem we are trying to solve is, given a particular weight, what is the probability of one class or the other class? Once we find these posterior probabilities and find out which one is higher, we can give our verdict as to which class is more likely. In this formula, we see P of x in the denominator, which we can calculate using the expansion we described before. Let's review some conventional terms used to define different components of this formula. We are trying to find the posterior probability. The class conditional probability is also known as the likelihood. The background distribution is known as the prior, and the probability of the observation itself, regardless of the class, is called the evidence. As I noted before, the class conditional probabilities by themselves are not enough to make a decision with. If, say, 70% of walnuts are fresh and 30% are rotten, we have to scale their likelihoods with 0.7 and 0.3 and use the posterior probabilities to make a decision with. We can claim from this figure that if the weight of a walnut is greater than 1.5 grams, it is more likely to be a fresh walnut, and if it is less than 1.5 grams, it is more likely to be a rotten walnut. One simplification of the Bayes formula we can do is to remove P of x from the denominator, because it is the same value for each class. Evidence P of x is just a scaling factor to ensure that the sum of the posteriors add up to 1. If our goal is to just figure out which one is larger, we don't really care to ensure that they add up to 1. So we'll skip the extra work and not bother dividing them with P of x. After we drop P of x from the denominator and compare for the two classes, we come up with a Bayes decision rule that says if P of x given W1 times P of W1 is greater than P of x given W2 times P of W2, then we would decide on W1 class. Otherwise, we would pick the other class. We can rewrite this rule as a likelihood ratio, where we would calculate the ratio of the posteriors, and if this likelihood is greater than 1, which would mean the posterior of the first class is larger, we would classify into the first class. Otherwise, we would classify this sample into the second class. We could rephrase the classification problem as a problem where we are trying to minimize the probability of making an error. The probability of making an error would then be the probability that the sample was really from class 1, but we had decided on W2 and vice versa. In this formulation, the probability that we have made an error would be equal to the smaller of the two posterior probabilities. If, say, posterior of W1 is 0.9 and the posterior of W2 is 0.1, we would have picked 0.9 because it was larger. But we would also note that there is 10% chance that we have made an error. Bayes' decision theory can be extended to incorporate cost functions. Suppose I hate cilantro and find its taste comparable to the scent of a dirty dish rag that clings to your hands. If I pick up cilantro and think it's parsley and put it in my mouth, I would instantly regret my decision. On the other hand, if I pick up parsley and think it is cilantro, in which case I would put it right back, I would not regret my incorrect decision as much. After we associate a loss function for each decision, we can formulate the classification problem as a problem where we are trying to minimize the overall risk. The risk of an action is defined as the cost of an action given that the item belongs to one of the classes multiplied by the posterior probability of that class, summed over all possible classes. Having calculated the risk of each action, our decision would be to select the action with minimum overall risk. The Bayes decision rule is not limited to two classes and can be applied to multi-categorical classification tasks as well. The posterior of the ith class is calculated as before, but now instead of having just two classes, the denominator is expanded over all possible classes. Again, for convenience, we can drop the denominator because it will be the same value for all classes. Another common transformation is to work in the log scale, so the discriminant function for the ith class can be written as the logarithm of the likelihood plus the logarithm of the prior probability. The process can be viewed schematically as shown here. Given D features such as weight, height, color, etc., we would calculate a discriminant function for each class. If the problem dictates the use of cost functions for each action, we can incorporate them into the discriminant functions as scaling factors. The discriminant function with the largest value would then determine our final classification. When we have only two classes, we can create a single dichotomizer function by subtracting the two discriminant functions. If g of x is greater than 0, we would pick the first class, and if it is less than 0, we would pick the second class. We can rewrite g of x as the log of likelihood ratios plus the log of ratios of the priors, and we get a formula that is more pleasant to look at. The interpretation of the prior probability is straightforward. It is a single number, which can be calculated as the fraction of the items belonging to one of the classes in the entire population. But the formulation of the likelihood is not as trivial. Intuitively, the probability would look like a histogram of x values in each class, such as the distribution of weights in the members of the first class. Perhaps the most practical model for the likelihood is to assume a normal distribution. A normal distribution, also called a Gaussian distribution, is a parametric distribution model described by two parameters, the mean and the standard deviation. The mean of a distribution is defined as its expected value. For instance, the expected value of a die roll is the summation of each number that we can get in a die roll multiplied by its probability, which is 1/6. and that's equal to 1 times 1 over 6 plus 2 times 1 over 6 all the way to 6 times 1 over 6, which gives us 3.5. The expected value of a die roll is 3.5. The variance is defined as the average squared spread around the mean. The standard deviation is found as the square root of the variance. The entropy of a distribution is defined as the negative sum of the probability multiplied by the log of the probability. The entropy, or disorder, quantifies the amount of uncertainty in the values of randomly selected points from a distribution. The Gaussian distribution has the maximum entropy among all distributions having a given mean and variance. In practice, Gaussian distribution is good for modeling phenomena where there is an ideal prototype pattern plus noise from a large number of random factors. Since normal distribution is the most commonly used model, let's explore how the Bayes decision theory works out for a class conditional probability that follows a normal distribution. Applying the Bayes rule to a normal distribution is just a matter of plugging in the Gaussian probability density function. The PDF of a normal distribution is shown here. When we calculate the posterior, again, we can drop the denominator because it will be the same value for all classes. Taking the logarithm gives us a more pleasant form of the PDF. In a univariate classification problem where each class is modeled using normal distributions, we would calculate the discriminant function for each one of them using their own specific mean and variance and find out which one has the largest value to give us the final classification. In a multivariate distribution, things are slightly more complicated. Rather than having a single mean, we have a vector of numbers giving us the mean of each feature. And rather than having a single variance value, we have a covariance matrix, where the diagonals describe the variance within each feature, and the non-diagonal values describe the interaction or the covariance between different features. If the features are statistically independent, then their covariance would be 0, and the covariance matrix would consist only of the diagonal values which represent the variances of these independent features. Things would get pretty messy quickly if we try to handle general covariance matrices, so let's make some simplifying assumptions to study the characteristics of the classification. Let's assume that the features are statistically independent and have the same variance value, giving us a covariance matrix with the same variance value on the diagonal and zeros everywhere else. We'll call this independent and identically distributed features. Unlike the univariate case where we used arithmetic operations, here we use matrix operations when we plug in the multivariate PDF. The letter T here represents the transpose of a vector. The inverse of a covariance matrix, that is sigma squared times identity matrix, is just identity matrix divided by sigma square. The identity matrix has no effect in multiplication here, so it can be dropped out. Multiplying the transpose of a vector with itself gives the norm of the vector, and expanding that gives us this formula. When we write this out for each class, they would each have their own specific sigmas and their own means. Let's make one more simplifying assumption and assume that each class has the same sigma value. So the only thing that's different among classes are the mean vectors and the prior probabilities. When the sigmas are the same for each class, we can drop this term and this term because they would be the same value for all classes. With the assumptions that the features are independent and identically distributed, and that different classes have the same sigma, meaning they have the identical class distributions, we end up discriminant functions in this form. which is a linear function of x. Let's call this term ai, which is kind of a slope, and the remaining term ai0, which is kind of an intercept. The points at which the discriminant functions of two classes are equal would form a hyperplane, such as a line in 2 dimensions and a plane in 3 dimensions. If the variance is relatively small compared to the distance between the class means, the prior probabilities won't contribute much in comparison to the location of the boundary. If we further restrict the problem to classification between only 2 classes, the decision boundary can be obtained by solving for the points where g1 is equal to g2, giving us this set of points. Let's examine what this solution looks like in different dimensions. In one dimension, where we are dealing with a single feature such as weight, the decision boundary is just a single threshold, a single point, such as x equals 1.9. In 2 dimensions, the boundary separating the 2 classes is a line, and in 3D, it is a plane. If we relax the assumption that the features are independent, but maintain that each class has the same covariance, we would find out that the discriminant function is again linear. If we remove the identical covariance assumption, the discriminant function becomes a quadratic function, and the decision boundary can take on the form of planes, spheres, ellipses, parabolas, or hyperbolas in multiple dimensions. With multiple classes, these decision boundaries can take on very complex shapes. As an example problem, suppose we have 2-dimensional data, meaning we have 2 features, and we are trying to distinguish between 2 classes. Suppose we are given some sample data to build our model with. Here we have 4 black samples from one class and 4 red samples from the other class. And also assume that the prior probabilities of the 2 classes are equal to each other. And we'll assume that the distribution of the samples in each of these 2 classes can be modeled by a normal distribution. We would first find out the mean and the variance of the normal distributions for each class, which gives us these means and these variances. After that, we can plug into the general form of the discriminant functions that we outlined earlier, which would give us quadratic formulas for each of the discriminant functions. In order to find the decision boundary, we would write down the discriminant functions for each class and set them equal to each other and solve for x, which gives us this parabolic formula. Based on this decision boundary, we would classify any sample above the parabola to belong to the black class and any sample below the parabola to belong to the red class. To summarize this lecture, we learned that a classification problem can be solved using the Bayes formula if we have a probabilistic model of the likelihood of obtaining a particular measurement given a class. While the Bayes decision theory works well for a small number of features, it is usually not practical for high-dimensional problems due to the lack of a good representative probability model to capture the distributions of samples across this high-dimensional space.